Hi everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the February-March exam for paper 6 in Physics IGCSE. The first question in this exam says a student determines the diameter of a marble by two methods and calculates the density of the material from which the marble is made. Some marbles are shown full size in figure 1.1. Question A says on figure 1.1 measures the length D. So we're going to use a ruler to measure the distance, 0 at one edge of the arrow and the other edge reads 7.8 centimeters. So this is the answer. Then says using your value of D, calculate the average diameter D1 of one marble. So we have here 5 marbles, so we divide 7.8 by 5. This gives us an approximate value of 1.56 centimeters. We can say approximately it's 1.6, so we keep the significant figures the same. Question I says suggest why it is more accurate when using a ruler to measure D for 5 marbles rather than measure the diameter for a single marble. The answer for this question is always to reduce percentage error. This means that the percentage error in a large reading is much smaller than the percentage error in a small reading. Method 2 in question B says figure 1.2 shows 2 wooden blocks and one of the marbles. Describe how the student uses the 2 blocks and the marble to determine a new accurate value for the diameter of a marble. Draw a diagram to show the arrangement. Describe clearly how the student ensures that the value for the diameter of a marble is as accurate as possible. In this case, we can draw a ruler as a rectangle and the 2 blocks as 2 rectangles next to each other and the marble as a circle in between. And we're going to say that the edge of the first block is reading 1 or R1 and the other one is reading 2, R2, and the diameter is the distance between the blocks. We can call it D, and we just say that D is equal to R1 minus R2 or R2 minus R1. Either way, if the 0 is from the left side, it's R2 minus R1. If the 0 from the right side, it's R1 minus R2. The next question says the student uses the top pen balance as shown in figure 1.3 to measure the mass of 5 marbles. He measures the mass M0 of a beaker without the marbles and then measures the mass M5 of the same beaker containing the marbles, 5 marbles, not 1 marble. It says record the values of M0 and M5 as shown on the top pen balance in figure 1.3. So the first one is 30.8 and the next one is 64.3 grams. The rest of the question says use these values to calculate the average mass of one marble. First, we need to know the mass of the 5 marbles. So we subtract 64.3 minus 30.8. Then we divide by 5 marbles. This gives an exact value of 6.7 grams. Question I says the student pours water into a measuring cylinder. He records the reading V1 of the water level in the measuring cylinder. That's water without anything. That's 26 centimeter cubed. The student places the 5 marbles into the water in the measuring cylinder as shown in figure 1.4. Record the new reading V2 of the water level in the measuring cylinder, which is in this picture. So we have here, it's below 40, so it's 30 something. This is 35, 36, 37. This is 38 centimeter cubed. Question I says, calculate a value for the average volume V of one marble. Again, we can subtract V2 minus V1. That's the total volume of the marbles themselves. But this is 5 marbles, so we divide by 5. So we are going to use the equation given to us here. So we have 38 minus 26 over 5. This gives 2.4 centimeter cubed. Next question says calculate a value for the density of the material from which the marble is made. Use your values of M and V from the previous questions and use the equation density equals mass over volume. So the mass we got for one marble was 6.7 grams and the volume for one marble in the previous question was 2.4 centimeter cubed. So we divide 6.7 by 2.4. This gives 2.791666 and so on. We're just gonna approximate to two significant figures, and the 9 rounds up the 7, getting 2.8 grams per centimeter cubed, and we're not required to write the unit, it's already given. Question D says, describe one possible source of inaccuracy in the method described in C and suggest one improvement to reduce its effect. One source of inaccuracy could be the apparatus itself. Maybe the measuring cylinder is not accurate enough, so it has a precision limit. Maybe the measuring cylinder is too wide, and we need a narrower cylinder to get more precision or more accuracy. So this is one reason. The measuring cylinder is too wide, and the improvement use narrower cylinder. Or we can say that water was lost due to splashing on the edges of the cylinder, and we can improve this by lowering the marbles gently or carefully using tweezers or using a thread into the water. Question 2 says, a student investigates the cooling of hot water from different initial temperatures. She uses the process shown in figure 2.1. There is a clamp holding a thermometer and there is a beaker. The thermometer is showing a reading. The student measures the room temperature. Record the room temperature theta R shown on the thermometer. This is 21 degrees Celsius. Describe one precaution that the student takes to ensure that the temperature reading is as accurate as possible. Since this includes a scale, then we say look perpendicular to the scale. This is to avoid a parallax error. Question B says, experiment A, the student pours a volume of 100 centimeter cubed of hot water into the beaker and records the temperature theta A at time equals 0 seconds. She records the temperature of the water in the beaker every 30 seconds. Her readings for experiment A are shown in table 2.1. Experiment B, the student repeats the process. She waits until the initial temperature theta B of the water is the same value as the temperature theta A at 90 seconds. So this is 90 seconds. This is the temperature of beaker A at 90 seconds. And this is the initial temperature of beaker B, and we have it empty here. In the first line of the table 2.1 record, her initial temperature theta B for experiment B. So we take this value and we put it here, 85.0. Her readings for the remainder of experiment B are shown in table 2.1, and always check the tables for the units of the headings. Here we have all the units, so we don't need to fill in anything. Then in question C says, write a conclusion stating how temperature at t equals 0 seconds affects the rate of cooling of the water. Justify your answer by reference to the values from the results. So at time 0, A started from 92 degrees Celsius and B started from 85 degrees Celsius. And they both took 180 seconds. So to judge the rate of cooling, we need to subtract the initial and final temperatures of each experiment to know which one cooled faster. So for A, we can subtract 92 minus 80. That gives us 12 degrees Celsius. For B, we subtract 85 minus 75. That gives us 10 degrees Celsius. This means that A was faster or had a higher rate of cooling, and it had the greater initial temperature. So we can say the higher the initial temperature, the higher the rate of cooling. So use the values in the table to reach a conclusion. Question DI says, calculate the average cooling rate called X1 during the second half of experiment A using the readings from table 2.1 and the equation X1 equals theta A 90, that means the temperature at 90 seconds, minus theta A 180, temperature at 180 seconds, divided by T, where T is 90 seconds and theta A and theta B are the temperature at 90 and 180. So we go back to the table. At 90 it's 85, at 180 it's 80, so we subtract 85 minus 80 and divide by the time 90. This gives an answer of 0.056, and we are required to write down a unit. We divided the temperature, which is in degrees Celsius, and time which is in seconds, so it's degrees Celsius per second. The double I says calculate the average cooling rate x2 during the first half of experiment B using the readings from table 2.1 and the equation theta b 0 and theta b 90 over t. T is 90 still. Theta b 0 and theta b 90 are temperatures at 0 seconds and 90 seconds. In the table we have at 0 seconds it's 85, at 90 seconds it's 79.5. So we subtract 85 minus 79.5, then we divide by the time 90. This gives us an approximate value of 0.061, also degrees Celsius per second. Triple I says a student suggests that x1 and x2 should be the same. They are not the same. One was 0.056 and the other was 0.061, but they appear close to each other enough. State whether your results support this suggestion. Justify your statement by reference to your results. So the statement, we cannot reach a statement until we make sure that these values can be considered equal, and for that we use the formula the larger number minus the smaller number over the larger number, and we get a percentage. We multiply it by 100. So the larger number 0.061 minus the smaller one 0.056 over the larger one 0.061, and you multiply this by 100, and this gives us 8.5%. As long as it is less than 20%, then it's acceptable. So the statement is yes. The results support the theory that x1 and x2 are the same because the difference between them is very small, or we say that the difference is within limits accuracy or experimental error. We go to question E. State two variables which must be controlled so that the comparison in x1 and x2 is valid or a fair comparison. We were comparing the effect of the initial temperature on the rate of cooling. So we keep those variable, but everything else we keep the same. So we can use same room temperature, we can use same type of container, same volume of water, any two of these. Now we go to question 3. It says a student investigates the properties of a resistance wire. He uses the circuit shown in figure 3.1. On figure 3.1, draw a voltmeter connected to measure the potential difference across the length L of the resistance wire. This is the length L, so we need to connect the voltmeter from the start of the wire to the end of length L at the crocodile clip. Then question BI says the student connects the crocodile clip to a length of 20.0 centimeters of the resistance wire. He measures the value of the potential difference V and the current I for the resistance wire, and the diagram shows the values. Read and record in the first line of table 3.1 in the next page the values of V and I shown on the meters in figure 3.2 and figure 3.3. First, we read this. From 1 to 2 there are 10 divisions, so every division is 0.1. So we have 1.1, 1.2, 1.3 volts, and we go to the table and we write down 1.3. Then we go back to the other diagram. Here from 0.8 to 1, that's 0.2 amperes, which means that every division is 0.02 amperes. So this is 0.82, 0.84, 0.86. So we go to the table and we write down 0.86. We go back to the page. The student repeats the procedure for length 40, 60, 80 centimeters and 100 centimeters of the resistance wire in turn. His results are shown in table 3.1. We just wanted to make sure that we didn't miss anything. Question double I for length 20 centimeters. Calculate and record in the table 3.1 the resistance R of the resistance wire using the values of V and I from the previous question, and we have the equation required. We divide the voltage by the current. We have 1.3 divided by 0.86. This gives an approximate value of 1.5 ohms. But the unit is already given in the column heading, so we don't need to write it. Question C says plot a graph of R per ohm on the y-axis against L per centimeter on the x-axis. Draws a straight line of best fit. Always draw the best fit. And we check if we need to start the axis from 0 only when it says before the graph starts from 0 and 0, or you are required to get something called the y-intercept, which is not here, so we don't need to start our graph from the origin. Now we have on the y-axis the values of R. We can get the scale using a very simple method. We take the greater number, the maximum number, and subtract from it the minimum number, and divide by the number of large divisions on this axis, which is here. We have 1, 2, 3, 4, and 5 divisions. That's the 10 square divisions. We divide by 5. This gives us a value of approximately 1.357. Then we have to compare this with either 1 or 2 or 5. These are the allowed divisions in graphs. So you either go 1, 2, 3, 4, or 2, 4, 6, 8, or 5, 10, 15, 20, and so on. So 1 cannot be used because it is smaller than the given number. 2 is just large enough. So we are going to use 2 to make the graph as full as possible. But since the first reading is 1.5, we have to start from 0 to get 1.5. So we have 0, 2, 4, 6, 8, and 10, but we're not going to use it. And the y-axis should be labeled R per ohm. As for the x-axis, it's easy because it's already in twos, in a scale of twos. 20, 40, 60, 80, 100. It's the same as 2, 4, 6, 8, 10. So we are going to use that scale, starting from 20, 40, 60, 80, and 100. And this is length per centimeters. Then we plot our points. The first point was 20 and 1.5. So we have 20 here, and this is 1. 1.5 is around here. The next point is 40 and 3.6. So this is 3, 3.2, 3.4, 3.6 is here. After that we have 60 against 4.2. So 60 and 4.2, this is here. Then 80 and 6.6. So this is 6.2.4.6 is here. The last one is 108.3. 8.2, 8.4, 8.3 is in the middle. Then we try to connect the first point with the last point and see if that gives us a best fit line. In a best fit, there should be some points above the line and some points below the line. In this case, it works nicely. We have the first one is on the line, the one next to last is on the line, and the last one is on the line. And we have 1 point here below and 1 point above, so we are good to go. So this is how the graph should look like. We should have the labels, and we have the method of maximum minus minimum over number of division, and then we compare with 1 or 2 or 5. In this case we chose 2, a scale of 2s. Then plotting the points as dot in circles or small x's. By the way, you can draw just a small x like that to mark the point. Then we draw a line of best fit, which should include at least 2 points from the table, and the rest are scattered, some above the line and some below the line. Question DI says determine the gradient G of the graph and show clearly on the graph how you obtained the necessary information. First of all, we need to choose 2 points on the graph. We cannot choose these points from the table because they are not on the line of best fit. For example, we have this point is already on the line, and we can choose another point that makes a good intersection with the graph grid, like this one, and we draw a triangle to point out which points we are going to use in our gradient calculation. So the first one is 80 on the x-axis and 6.6 on the y-axis. This is 0.2. Here we have 22, 24, 26 on the x-axis against 2 on the y-axis. So we have 0.1 and 0.2. Then we use the equation y2 minus y1 over x2 minus x1. So we have y2 was 6.6, y1 was 2, x2 was 80, x1 was 26. This gives a value of 0.085185 and so on. But we are going to approximate this to two significant figures. That's what the graph can give us. So we're going to say that it's 0.085, and the unit of the gradient is the unit of the y-axis, which was ohms, over the unit of the x-axis, which is centimeters. By the way, not all candidates can draw the same line. So the gradient usually has many values, and you get a fairly good range for your answer to be correct. Question double I says the gradient G is numerically equal to the resistance per unit length R naught of the resistance wire. Write down a value for R naught for this experiment. It just says that G is numerically equal to what is required. So we are going to copy the same number, which was 0.085, and it has the same unit ohm per centimeter. Question E says suggest one practical reason why the student carrying out this experiment may not obtain the same readings as in table 3.1. Assume that the procedure has been done carefully. First of all, we can look at the limitations of the experiment itself, or the diagram itself. Here we have a crocodile clip that determines the end of length L, and the crocodile clip is usually thick to pick just one number on a ruler. So we can say that it is difficult to determine the position of the center of the crocodile clip to measure L. Or we can say that the resistance of the wire keeps changing due to heat, or that it is not uniform across the complete wire. Now we go to the investigation question. In these questions, you can simply get enough marks by defining something called the independent variable and the dependent variable. Mainly there will be something that you would change yourself in the experiment and measure the other one. So you would change an independent variable and see what happens to the dependent variable. And if there are any variables or factors that can affect the dependent variable other than the independent, we keep these variables the same across the experiment, and we call them controlled variable. So if you just say how to measure the independent variable and an accuracy precaution, that's 2 marks, and how to measure the dependent variable and an accuracy precaution for it, that's another 2 marks, so 4. And mention one controlled variable, that's 5 marks. Then you draw a table and you either say compare values or mention any equation for calculation, or you say plot a graph of independent variable on x-axis according to which independent variable in this experiment, and the dependent variable on y-axis. So we read first the experiment. It says a student investigates the motion of a ball through the air. Plan an experiment which will enable him to investigate how the range of the ball depends on the angle at which it is launched. The range is the horizontal distance that the ball travels after leaving the end of the channel, shown in figure 4.1, and before hitting the ground. So the ball is supposed to roll down this channel and then goes up and then falls to the ground, and the range is the horizontal distance moved from the channel to the ground. The apparatus available includes a flexible channel as shown in figure 4.1, which can be bent at different angles, a selection of balls, each of different diameter and mass. In your plan, you should list any additional apparatus needed, explain briefly how to do the experiment. You may add to figure 4.1 if it helps. You don't need to start over the whole diagram. State the key variables that you keep constant, that's the controlled variables. Draw a table with column headings to show how to display the readings. You are not required to enter any readings. You are always not required to enter any readings unless it says sometimes enter specific values between 0 and 200. Explain how to use the results to reach a conclusion. That's you either plot a graph or compare numbers. But how to identify the dependent and the independent variables? We go to the sentence starting with plan an experiment, and we see the variables, which one affects the other. Here it says plan an experiment which will enable him to investigate how the range of the ball depends on the angle at which it is launched. So the range of the ball depends on the angle, which means this is the dependent variable and this is the independent variable. So we have angle and we have range, which was the horizontal distance that the ball travels after leaving the end of the channel. So now we need to identify a method to measure the angle of the launch, and we need a method to measure the range of the ball. An angle is usually measured using a protractor, and the range of the ball can be simply measured using a meter rule or a measuring tape on the ground, and we can see how to make these measurements more accurately. You don't have to write down everything, you can just simply draw it on the diagram. So for example, we can drop a dashed line here, and we mentioned that the ball will be rolling. So this is the ball, and you can draw it leaving the surface and falling here. And we say that this distance with the double-headed arrow is the range. We can call it D or X or R for range, anything you like. And we can just place a rectangle here and label it meter rule or measuring tape. And we can say that we are holding the channel using a clamp and a stand, or maybe 2 clamps and 2 stands for balance, and label them. You don't need to be an artist to draw these. These are just simple shapes, just lines and rectangles and squares or circles. And you can just stick a protractor to the edge of the channel like this and label it protractor to measure the angle. And you can label the angle here. For example, this part, you can label it as theta or anything, or alpha. And technically this is the experiment. Then you will say that you will release the ball and let it go off the channel, and then it will hit the ground at a certain distance. And we can say some accuracy precautions now for the measurements. For example, sticking the protractor as close as possible to the channel using a sticky tape or an adhesive material. And we can say to avoid bouncing of the ball, we can use some sand here, and we can just measure the center of the hole made by the ball when it falls on the sand. And since we put all this information on the diagram, when we write down the experiment, we just say set up the apparatus as shown in the diagram, and we can write the rest of the steps as bullet points. We can say stick the protractor to the channel as shown and measure the angle theta looking perpendicular to the scale. Then we release the first ball and measure the distance D to the center of the hole made on the sand. And just for accuracy, we repeat the distance measurement, repeat the previous step to get an average distance, D average, for example. And technically, we just finished the experiment. We then say that we repeat all the steps for other angles, but then we mention the controlled variables. What will we keep the same in the experiment? So we say repeat the above steps for different angles, but using the same, for example, ball height above the ground and inclination of the top of the channel. For example, if you make the inclination like this and then you use a greater inclination, this will cause the ball to go faster, and if the angle is different, it can go a different distance just depending on the angle of the channel, not the end of the channel. We finish the experiment, then we go to the table. We usually put the independent variable as the first column in the table, which is the angle theta, and the unit is degrees. Then you measure the distance 2 times. So we have D1 per centimeter, D2 per centimeter. Then we calculated an average distance in centimeters also. So these are the column headings, and we don't need to do anything more in the table, just the column headings, no values entered below the headings. And we can say that we are going to plot a graph of theta per degrees on the x-axis against the average per centimeter on the y-axis. You are not required to mention any expected conclusion. This is just a design for the experiment so that someone else can do the experiment and find out the relationship between the angle and the distance. So this was the end of this exam. I hope you do well in your exams, and I will see you in another video.